Welcome back. You should have just finished your graphing activity. Make sure that you submit that under today's assignment, as that is the only thing you're going to be submitting today. So make sure you submit that, and then we do have a couple more notes I want to go over, so you will need your note packet in front of you for the remainder of the class. So, a data table. What is a data table? Hopefully you know what a data table is. Hopefully you used them last year in chemistry. I know you would have in my class. Hopefully you did as well in Mr. Sulek's class. A data table is just a generalization of how you organize information. We're not going to be making a ton of data tables ourselves here in biology, especially in the online setting, but you will be reading data tables quite regularly. This is a pretty important skill to have, especially as we go to take the SAT and ACT. I think you guys take the SAT. But you will do a lot of reading of graphs. That is going to be a big push for this year, and especially in this unit of reading and interpreting graphs. So make sure you know how to organize a data table, make sure it's neat and lovely looking. Another thing we need to understand how to do is how to transform our data. So transformation is pretty important, as data is transformed to make it easier to understand and so that we can identify key features. So generally we transform data into percents, rates, and different frequencies so that we can better understand it. So for instance, body mass and mass pulled. So what if your body mass is 14 and you can pull a mass of 30, what percent of your body mass are you pulling? So when we first look at this data table, it looks like, oh, this person can pull the most, they pull 35 mass, and so they must be the strongest, but that might not be true because of the way this data table is set up. So what I'm going to do is shrink this screen a little bit and calculate these so that we can see if that's really true or not. So how do you think we would go about calculating the percent of body mass based on the body mass given and the mass pulled? So what is the percent of body mass that they're pulling? I believe how you do this might be wrong and my brain might be being stupid, but we're going to do 30 divided by 14 times 100. So this person is pulling 214% of their body mass, so quite a bit. We're going to do the same for the next person. 28 divided by 12 times 100. They're pulling 233% of their body mass, whereas person 3 is pulling only 194% of their body mass. So at times data can be deceiving in a data table if you don't transform it into something usable. So it appears that this person can pull the most, but in comparison to how big they are, they're the biggest, so they should be able to pull the most. And in retrospect, they are the weakest compared to how big their body actually is. So transformation of data can be pretty important in understanding how data is read and the final results. So I want you to take a look at these two things, both the data table and the graph, and what one do you think is easier? I think you'd be crazy if you said this crazy data table, because this is hard to understand. That's a lot of information coming in. This is clearly easier to read. You can see the general trends, you can see what we're looking at, you can see our axes, you can see everything very clearly, while this is very cluttered. So this is the importance of graphing. We're generally always going to make a graph from our data table so it's easier to read and understand. So I want you to think a moment, what are some important aspects of a graph? What do you need to have on a graph to make it a good graph? Hopefully you identify that you need a title. Your graph always needs a title. You need, I don't know why that is cut off. I'm sorry about that. You need axis labels. You need an x-axis, which of course is your independent variable. And you need a y-axis, which is your dependent variable. I don't know why that's cut off. I'm sorry, one moment. Let me move it. Better. Present. Sorry. Just going with the flow. I'm not restarting this video. Alrighty, we also could use a key. So in case we need it, we need to identify the differences in our graph. So we need a legend or a key to tell us what those differences are. And then we need clear labels and evenly spaced numbers on a scale. So something that's important to remember when making your graph is, does your graph talk? Does it have a title? Does it have axis labels? Does it have does it have access? Does it have labels on your access? Does it have a key? And does it have a correct scale? So think about those 5 things when you're making your graph. I want you to go ahead and look over that graph that you made earlier this week about the chimpanzees. Did you include all of those things in your graph? Yes or no? If you didn't, go ahead and fix it up. So, analyzing data. Make sure you're reading your graphs closely. This is super important. Don't just look at a graph and assume what it's telling you. You always need to read the title first. Always read your title first so that you know what you're looking at. Make sure you're reading the keys and the labels so you understand the difference between things. Make sure you see what graph is, or what line is for males and what line is for females. What bar is for males or for females. Notice that all 3 of these pieces of graphs show the same amount of data, just in different ways. Again, read the title. Estimate when possible. And extrapolate, which means predict information based on your given data. So I want you to take a moment and look at these 3 graphs. Which one do you think is easiest to notice information on? I personally think a bar graph is very easy to see in this specific example. Pie charts are generally kind of confusing, and pie chart is generally not something you use in biology, but you will use a lot of line graphs as well. So I'm going to tell you how to know when to use different types of graphs. So a line graph is continuous data when one variable is affecting another. So they're directly correlated. One thing is affecting the other. Generally, it's time and trials and number of data and that. It's generally over a series of time. A bar graph is when you have non-numerical data for one variable. So notice in this example, you have the nicest fruit. The apple is the non-numerical data, where the number of people is the numerical data. You can use a scatter plot when there's continuous data within a relationship between variables. So the total bill versus the tip. And then a histogram is the frequency of distribution. You will only use a histogram when the word frequency is present. If you see the word frequency, make a histogram. And a histogram is just kind of a fancier bar graph that uses numbers on both axes, but frequency is always going to be your y-axis. And notice a histogram looks just like a bar graph, but there's no spaces between the bars. So I'm not going to go over lab protocol because you aren't going to be doing labs in class. So this is actually all you're going to be completing today. So you are all good to go. Make sure you submit that graphing activity from earlier today, and then you are done for the day. Thank you.